In this case, we look at a compound body in which we have a rectangle with a particle attached to it. Let's look at a uniform rectangular lamina ABCD, where AB is 6 and BC is 4, and the mass is 2m. Particle of mass m is attached to the rectangle at B. So we now have a compound body. This body is freely suspended under gravity from E, the midpoint of AB. Find the angle made by AB with the horizontal. Well, let's get this information onto a diagram. Of course, a large diagram. We want the center of mass of the rectangle. Well, the rectangle is 6 by 4. If the rectangle is 6 by 4, that means that this length is 3. Woohoo, it's moving. This length is 3, that length is 3, and this is divided into 2 and 2. Well, our center of mass is going to be in the central point of the rectangle. That's not very central. Let's make it a bit better. There. So that will be our center of mass of the rectangle. It will be a distance of 2 straight down from E. And at that point, we consider the mass of the rectangle all concentrated at the one point. We think of it as 2m. And if we are hanging this vertically under gravity, we can think of a force downwards of 2mg. We've got a mass m attached to the rectangle at B. And we can think of a force downwards, therefore, of mg. And we are asked to find the angle that AB makes with the horizontal. So let's draw a horizontal. We want that angle, which I'll call theta. Well, in this case, I prefer looking at moments. If we take moments about the point E, we can ignore the tension in the string because the string is passing through the point, it has no moment. mg will have a clockwise moment, and the 2mg will have an anti-clockwise moment. They must balance each other out. And this is where we need to think of moments as the moment of a force is the magnitude of the force times the distance from the pivot to the line of action of the force. So we actually want the length of that green line, the distance from the pivot to the line of action of the force. So let's have a look at that. If we just make up a right-angled triangle, then we are looking at the distance, let's say EK, and the distance EK, let's have K in blue. The distance EK is just 3 cos theta. Okay, so that side of it, we can work out the moment there. It's going to be 3 cos theta times mg. Let's look at the other side. We want the distance from the pivot to the line of action of the 2mg. Here's the 2mg, the line of action is there. We need this line here. Well, let's call this point, let's draw a line in first, there to make up a line triangle, and let's call this point N. Then we want the length of EN. Where is theta in all this? Well, theta is the angle here, which if we go opposite, that is the angle theta as well. This one must be 90 minus theta. If that's 90 minus theta down here, we must have an angle of theta. So let's put theta in. Oh, it's going in blue, but never mind about that. And then the length of EN is going to be 2 sine theta. So now we're in a position to take moments. If we take moments about E, we will get the clockwise moment, which is EK, which is 3 cos theta. So you've got 3 cos theta times mg, force times distance to the line of action of the force, is equal to the anti-clockwise moment is going to be the length of En, which is 2 sine theta, times 2mg. Various things cancel, and we're left with 3 cos theta is equal to 4 sine theta. If we therefore divide both sides by cos theta and divide both sides by 4, we get 3 over 4 is equal to tan theta, and therefore theta, the angle made with the horizontal, is equal to 36.9 degrees. You won't find an example like this in your textbook, but you are expected to be able to do this sort of problem, and you will find a note on this in the website.